Welcome to Understand All. I'm your host, Aslakir Gerleif. Today, we're embarking on a mind-bending journey into the quantum realm to explore one of the most fascinating theories in modern physics, loop quantum gravity. Imagine for a moment that the fabric of space-time isn't a smooth, continuous sheet, but rather a complex network of tiny, interwoven loops. This is the captivating idea at the heart of loop quantum gravity, or LQG for short. It's a theory that challenges our fundamental understanding of the universe and promises to revolutionize our perception of reality itself. But before we dive into the intricacies of LQG, let's take a step back and understand the problem it aims to solve. You see, two of the most successful theories in physics, quantum mechanics, and general relativity, have been at odds with each other for decades. Quantum mechanics describes the bizarre behavior of subatomic particles, while general relativity explains the large-scale structure of the universe, including gravity. The trouble is, these two theories just don't play nice together. It's like trying to fit a square peg into a round hole. It just doesn't work. This is where loop quantum gravity comes in. It's a bold attempt to reconcile these two pillars of physics and provide a unified description of space, time, and gravity at the quantum level. And let me tell you, the implications are nothing short of mind-blowing. At the heart of LQG is the idea that space-time is not continuous, but rather composed of tiny discrete units called loops. These loops are incredibly small, on the order of the Planck length, which is about 10^35 meters. To put that into perspective, if an atom were the size of the observable universe, the Planck length would be roughly the size of a tree. According to a paper published in the journal Physical Review Letters, these loops of spacetime are thought to be about a billionth of a billionth of a billionth of a billionth of a centimeter across. Now, I know what you might be thinking. How can something so small have any impact on the universe we observe? Well, that's where the magic of quantum mechanics comes into play. Just like how atoms, despite their tiny size, give rise to the incredible diversity of matter we see around us, these quantum loops of spacetime could be the building blocks of everything we know and love. One of the most exciting predictions of loop quantum gravity is that spacetime itself is not fundamental, but rather emerges from the complex interactions of these tiny loops. In other words, the smooth, continuous fabric of spacetime that we experience is just an illusion, a macroscopic average of the quantum geometry beneath. It's like how a seemingly smooth beach is actually made up of countless grains of sand. This idea of emergent spacetime has profound implications for our understanding of the universe. For one, it could solve the long-standing problem of infinities that plague other attempts to quantize gravity. In LQG, the discrete nature of spacetime effectively smooths out these infinities, providing a more mathematically consistent framework. But that's not all. Loop quantum gravity also offers a fresh perspective on some of the most perplexing phenomena in the universe, such as black holes. According to LQG, black holes are not the infinitely dense singularities predicted by classical general relativity, but rather have a finite quantum structure. In fact, a recent study published in the journal Physical Review X suggests that black holes in LQG may have a quantum hair, a subtle quantum-level property that could help resolve the infamous black hole information paradox. And if you thought black holes were mind-bending, wait until you hear about the Big Bounce. In the standard Big Bang model, the universe is thought to have originated from a singularity, a point of infinite density where the laws of physics break down. But loop quantum gravity paints a different picture. Instead of a singularity, LQG predicts that the universe underwent a quantum bounce, a moment when the immense gravitational forces at play were counteracted by quantum effects, causing the universe to rebound and expand anew. It's like the universe is playing a cosmic game of basketball, bouncing back from the brink of collapse. This idea of a cyclical universe, endlessly expanding and contracting, is not only aesthetically appealing, but also avoids the thorny issue of the initial singularity. It's a testament to the power of loop quantum gravity to provide fresh insights into age-old cosmological questions. But of course, no theory is without its challenges, and LQG is no exception. One of the biggest hurdles is finding ways to experimentally test its predictions. Because the quantum effects of gravity are so incredibly tiny, detecting them directly is a daunting task. However, scientists are not ones to back down from a challenge. Researchers are exploring clever ways to indirectly probe the quantum nature of spacetime, such as looking for subtle deviations in the cosmic microwave background radiation, the afterglow of the Big Bang. Another avenue of investigation is the study of black hole evaporation. As Stephen Hawking famously discovered, black holes are not entirely black. They emit a tiny amount of radiation over time, slowly evaporating away. The precise nature of this evaporation could provide clues to the quantum structure of space-time. According to a study published in the journal Classical and Quantum Gravity, the spectrum of radiation emitted by black holes in LQG may differ from the predictions of standard quantum field theory, offering a potential observational test. But perhaps the most exciting aspect of loop quantum gravity is its potential to revolutionize our understanding of the very nature of reality. If spacetime is indeed quantized, it could have profound implications for how we think about causality, determinism, and the flow of time itself. It's a theory that invites us to question our deepest assumptions about the universe and our place within it. As we continue to explore the quantum realm, loop quantum gravity remains a tantalizing contender in the quest for a theory of everything. Its elegant mathematical framework, coupled with its bold predictions and philosophical implications, make it a theory worth paying attention to. Who knows what secrets of the universe it may yet unveil? So the next time you look up at the night sky, remember that beneath the twinkling stars and the vast expanse of space lies a hidden reality, a quantum world of tiny loops and infinite possibilities. And as we venture deeper into this strange and wondrous realm, we may just find the answers to some of the most profound questions of our existence. In the words of Carlo Rovelli, one of the pioneers of loop quantum gravity, science is not about certainty. Science is about finding the most reliable way of thinking at the present level of knowledge. And that, my friends, is the beauty of scientific exploration, the endless pursuit of knowledge, the willingness to question our assumptions, and the courage to imagine the unimaginable. As we wrap up today's journey into the captivating world of loop quantum gravity, I encourage you to keep an open mind and never stop wondering. The universe is full of mysteries waiting to be unraveled, and who knows what groundbreaking discoveries await us in the quantum realm. Until next time, stay curious and keep exploring the wonders of the cosmos.